In this opportunity, we're going to discuss about how to find the pH for strong and weak acids. And in this opportunity, we are going to start making those ice tables to work acid equilibrium. For the most part, acid equilibria it's a little easier to work because the stoichiometry is very simple. But we will see that as we move through the material. Okay. First, let's talk about the percent ionization, which is yet another way in which you can refer to the strength of an acid. So the percent ionization is telling you how much of the acid is dissociated, how much of the acid is ionized in solution. So let's say you have 100 molecules of the acid, you put it in water, and then 5 of those molecules undergo ionization. Then you say, well, the percent ionization is 5% because 5 out of 100 molecules of the acid are ionized. So because pretty much the amount of acid that is ionized is present as the hydronium ion and the conjugate base, then that fraction of the acid that is ionized is equal to the concentration of hydronium ion. So that's what we have here. The ionized acid, that concentration of the acid that is ionized would be equal to the concentration of hydronium ion. These are at equilibrium, but we can simply put it this way. Hi ionized is equal to H3O plus or H plus, however you're gonna see it. Okay, and that comes from the fact that, remember, our our standard acid equilibrium, if you will, is H plus plus A minus. Okay, so this is our percent ionization. It's another way which we can express strength of an acid or a base. I mean, we can apply the same concept to a base. And the higher the percent ionization you have for a particular substance, then it means the stronger that substance is, being an acid or being a base. Now, when you have strong acids or strong bases, remember they are completely ionized. Therefore, whenever you add this acid or this base, the concentration of H plus that you're going to have in that solution is going to be equal to the concentration of acid that you are adding. So let's say if you have HCl and you prepare HCl 1 molar, then that means that the concentration of H3O plus is 1 molar. Okay, why? Because HCl goes H plus plus Cl minus. And notice here that this is just a single arrow. There is no an equilibrium arrow because hydrochloric acid doesn't have an equilibrium. It completely dissociates. If it completely dissociates, then there is no equilibrium. There is no amount of the original HCl that is present as the whole molecule. So that's the rationale behind this. So remember that when you add these substances in water, you are talking about the hydronium ion, the hydroxide ion, and there will always be at least 2 sources of those ions. The acid or the base that you're adding and water. So the thing that you have to consider here is that if you have pure water, then the concentration of H plus and the concentration is equal to the concentration of OH minus, and that's equal to 10 to the negative 7. So normally when you add an acid, no matter how small the quantity of an acid, if it's strong acid, then the acid dominates. For example, HCl, even if you prepare 10 to the negative 3 molar of acid, which is a very diluted acid, here the concentration of H plus is going to be 10 to the negative 3, which is much larger than the contribution from water. That means that when you are adding acid, and the same goes for a base, they will dominate the that particular ion. So the contribution from the strong acid to the hydronium ion would be so large that you can pretty much ignore the contribution of water. Is that all the time? Well, for strong acids, you can pretty much assume that. For weak acid, well, not so much. So once again, here we have yet another case in which, remember this, do you have strong acids? These are monoprotic. This is a diprotic acid. And when you work acid-base equilibrium, you always do it one step at a time. And that's going to make sense in a little moment. Okay, but nonetheless, here we have hydrochloric acid, 0.1 molar. The concentration of the hydronium ion is 0.10 molar as well. And when you take, remember, for pH, you take the negative log of 0.1, and that's going to be pH 1. Okay. The only thing I want to say about, for example, sulfuric acid is that one step at a time, right? So think of diprotic as a two-step ionization. Okay. So for example, for sulfuric acid, the first step is H plus HSO4. Okay, and this is step 1, and step 2 is HSO4. It goes to H plus SO4 to minus. Every single acid, if you have more than one acidic proton there, more than one acidic hydrogen, they would you always write that ionizations in steps. You have 2 acidic hydrogens, it's 2 steps. If you have 3, then it's 3 steps. The particular situation with the sulfuric acid is that the first step is strong. So the first step, sulfuric acid is completely dissociated. The second step is weak. What does that mean? So when you come here, okay, so if you were assuming that sulfuric acid did this, 2H plus SO4 2 minus, then if the concentration of sulfuric acid was 0.10 molar, then that means that the concentration of H plus would be 0.2 molar. If both steps were strong acids, then the concentration of H plus would be 0.2 molar. But this is incorrect. So that is not the concentration of H plus. The concentration of H plus is a little smaller. Okay, it's larger than the 0.10 molar of acid sulfuric acid that you're adding, but it's not as large as if the sulfuric acid released all its protons. Okay, so in that case, in this opportunity, we are not gonna dig that deep into why the concentration is 0.1 molar. The point is that it's not as high as if both steps were strong for sulfuric acid. So therefore, concentration of H3O plus is 0.11 molar, and the pH is 0.96. So when you have a weak acid, then the story is a little bit different, because not all of the acid that you're adding will ionize, and what you have to use there then is Ka, right? So here, remember, we forget about water when we write Ka. Ka is equal to, and how about we scratch this and we say this is A minus. How about we scratch this and we say that this is Ha. So Ka is equal to H3O plus A minus divided by Ha. And it's a good thing that we have that expression like that, because for the most part, all acid-base equilibria, you can the stoichiometry of that equilibrium is technically it's always 1-to-1, so it makes calculations rather simple. So we have this case, it's 0.1 molar of HCN. Okay, whenever you have the whenever I give you this, for example in the exam I will give you anything that you need. In this particular case we need the value of Ka, and Ka for hydrocyanic acid is 4.90 10 to the negative 10. So 490 10 to the negative 10 versus 0.1, well, this is much larger, right? So remember the assumption that x small, well, we can do that assumption here. So we write the equilibrium, HCN goes to H plus. For simplicity, I'm just going to stick to H plus. Cn minus, okay, our ice table. And I promise you this, once you have done enough ice tables with acid-base equilibrium, you will not do it, okay? 0.1, 0, and 0. The acid is dissociating, so that's minus x. You're producing H plus and Cn minus plus x, all stoichiometry is 1 to 1. So at the very end you have 0.1 minus x, x, and x. If Ka is concentration of H plus, concentration of Cn minus over concentration of HCN, then we end up with x squared 0.1 minus x. But because we already decided that the approximation x small is valid, then we can forget about this x. And our expression for the constant will be 0.1 Ka equals x squared. Therefore x is square root of 0.1 times 4.90 10 to the negative 10. And this is equal to, x is equal to 700 10 to the negative 6. Okay, this is the concentration of H plus. It's not a question, but what if we wanted the pH? pH is minus log of 7 10 to the negative 6. And this is going to be equal to 516. Okay, so it's rather simple. Here we have a table of several acids. Do you have to memorize the table? Well, not really. So if you're doing exercises, then these come handy in terms of getting the information, whether you need the pKa, whether you need Ka, or just review what the acid is. But in terms of structure, you don't really need the structure of an acid. Why? Because now we have hydrofluoric acid, and hydrofluoric acid is rather simple as well, but what I mean is all acid equilibria can be written as HA, H plus, A minus. Every single one. So you don't really need a structure. The only thing that you need to know is whether you have 1, 2, or 3 acidic hydrogens in the acid, and then you can write everything that you need in terms of that basic equation. However, here for hydrofluoric acid, okay, H plus fluoride. For hydrofluoric acid, Ka is 6.8 10 to the negative 4. So you're comparing 0.250 versus technically 10 to the negative 4. So you are about 3 orders of magnitude there. So we are good in terms of the approximation. So no surprises here. When you write your ice table, this is 0.25, 0, and 0. The change for hydrofluoric acid is minus x. The change for H plus is plus x and plus x. So we have 0.25 minus x, x, and x. The expression for Ka is the same, so we can skip writing the initial. Ka is going to be x squared 0.25 minus x. Okay? And because we are assuming that x small, then we forget about x, and we end up with x being equal to the square root of 0.25 Ka. This is equal to square root of 0.25 6.8. 6.8 10 to the negative 4, and this is equal to 0.013. You compare 0.013 to 0.25, and really you will end up with 0.24, okay, instead of 0.25. So the change is really small for the concentration of hydrofluoric acid. You can assume that it's practically the same as the initial. pH minus log of minus log of 0.13, and this is equal to 188. Okay, so but not all the time you can assume that because the approximation is valid. You will come across times in which, well, you have to consider it. So in this particular case, we have chlorous acid, and for the chlorous acid, the Ka is equal to 0.011. Now you compare this value to this one, and it's about 10%. 10% difference between Ka and the concentration of acid tells you that at best the value of X would be about 10%. So that's about the 5% that we are looking for, right? So from the get-go, we already know this is not going to work. We have to do the full quadratic equation here. So this is the acid, but we can write the equilibrium as HA goes to H plus A minus, and we are not losing any kind of information here. Not because you don't write the formula of your acid means you have to. Your analysis will not change a bit just because you don't use the formula of your acid. So initial conditions, 0.1 molar of the acid, 0 and 0. The change, always 1 to 1, minus X, plus X, plus X. At the end, you have 0.1 minus X, X, and X, right? So Ka is equal to X squared, 0.1 minus X. However, here we cannot get rid of that X on the denominator, so we have to keep it. So if we multiply by 0.1 minus X at both sides of the equation, then we have 0.1 minus X, Ka equals X squared. And this becomes 0.1 Ka minus Kax equals X squared. If we continue manipulating this equation, then we will end up with X squared plus Kax minus 0.1 Ka. Okay, and at this point you can use whatever method you have for calculating a quadratic equation. You can use the formula, you can use a calculator. There is no way I can prevent you from using a graphic calculator to solve this. So if you solve for X, and let's complete this, right? So X squared plus 0.011 X minus 0.1 times 0.011 is 0.0011. This is equal to 0. If you solve for X, then you will obtain X1 equals minus 0.0391 and X2 equals 0.0281. Okay? Now this will represent concentration of H plus. But guess what? There are no negative concentrations. So whenever you have that situation, usually you will get a negative root and a positive root. You keep the positive one. Okay, so the concentration of hydronium is 0.0281. The pH in this case is minus log of 0.0281. and that is equal to 155. Now, one thing to notice here is that you have to compare this number 0.0281 compared to 0.1. This is about 28%. 28% difference that you have for the acid. So it's a significant impact on the concentration of the acid. Okay, so that Ka is rather large. How about we do another one? So in this particular case, we have nitrous acid. The Ka for nitrous acid is 4.6 10 to the negative 4. Now you're comparing 0.01, so you're comparing 4.6 10 to the negative 4 versus 10 to the negative 2. It's a little less than 100 times. Okay, so you are kind of borderline. So let's treat this problem as if it was a not valid assumption. Okay, so again, your acid, and this is what I really mean when you will not need the ice table as much as you think. Because you can do this, every single acid equilibrium can be written in those terms. Again, no surprises here. Initial 0.01, 0 and 0. The change minus x plus x and plus x. The equilibrium 0.01 minus x, x and x. So I believe you are start seeing a pattern here. You can always, even without writing the ice table, you can come up with the conclusion that Ka is x squared 0.01 minus x, and this is the initial concentration of the acid. Okay, there would be situations, and a little more complex situations, that I still have to think whether we're going to go there, but this is the basic setup. Okay, so if we manipulate this expression, okay, and I'm going to let you do that, you will end up with x squared plus Ka x minus 0.01 Ka. If you solve for this, you will obtain minus 0.00239 and 0.00193. Which one you pick? You pick the positive one. Okay? You pick the positive one, and pH, if you want to do that, is going to be minus log, because this is the concentration of H plus, minus log of 0.00193, and that is equal to 271. What if we want to go in the other direction? What if at this point we've been using the initial concentration of the acid and the acidity constant to find the pH of the solution? What if you have the pH and then you want to find what the value of Ka is? Well, that's actually not that hard to do, because what is Ka? Ka is equal H plus A minus divided by HA. Pretty much if it's a weak acid, for the most part you can assume that HA is the initial concentration of the acid, and H plus would be equal to A minus, and H plus, if you have the pH, then is equal to 10 to the minus pH. That means that in this particular case, H plus is equal to 10 to the negative 425, and this is equal to 562 10 to the negative 5. Okay, that means that Ka, let's use a different color here, Ka is going to be equal, because these two concentrations are equal, then is equal to 562 10 to the negative 5 squared divided by 0.1. Okay, if you subtract 562 10 to the negative 5 from 0.1, you basically are going to obtain 0.1. Okay, so Ka here is 316 10 to the negative 8. Okay, so what I was saying is that before, so 0.100 minus 0.0000562, which is this number, this is equal to 0.9994, and I don't know you, but to me this is pretty much 0.1. Okay, so there is no a big impact there. It's a concentration rather small that makes you feel as if the initial concentration of acid didn't change. Let's do another one. So in this case we have the concentration of H plus is going to be 10 to the negative 325, and this is equal to 562 10 to the negative 4. And 562 10 to the negative 4 compared to 0.175, you can still assume that is rather small. So in this particular case then, Ka is equal, again, the concentration of H plus, okay, they are equal. That's why here on top, when we do this, you get a square divided by the initial concentration, which is 0.175, and this is going to be equal to 1.8 10 to the negative 6. Okay, this is Ka. What if we wanted to know what the pKa is? Well, pKa is minus log of Ka equal minus log of 1.8 10 to the negative 6, and this is going to be equal to 574. Okay, so this is the pKa of that acid. Now in this problem we have percent ionization. In this case we're gonna use the percent ionization of a weak acid, and well, actually not use the percent ionization, but to calculate the percent ionization of the weak acid, and that percent ionization comes in the form of percent ionization is the concentration of H plus divided by the concentration of the acid times 100. So basically all we have to do here is to calculate what the concentration of H plus is based on the initial information, 2.5 molar of the nitrous acid, and if we remember correctly, Ka is 4.6 10 to the negative 4. And based on all the setups that we have been doing here so far, we always end up with an expression that tells you that Ka is x squared over initial concentration of the acid minus x. Regardless of the acid, whether Ka is small, whether you can make the assumption that x is small or not, you end up with an expression like that. Now you are comparing 4.6 10 to the negative 4 versus 2.5. And there are more than 3 orders of magnitude difference there. So we can assume that x is small. Okay? And if we do that, then x is going to be simply the square root of the initial concentration of acid times Ka. So x is equal to square root of 2.5 times 4.6 10 to the negative 4, and this is equal to 0.0339. Okay, that's the concentration of H plus. Therefore your percent ionization is going to be equal to 0.0339 divided by 2.5 times 100, and this is equal to 136%. So at that concentration, 2.5 molar of the nitrous acid, 1.36% of the molecules of the acid are ionized, are present as H plus and A minus. Okay, so that's the meaning of that number right there. Now, a more complex, if you will, situation is when you have mixtures of acids, because the thing that you may notice here is that you have three different sources. Each acid will represent a source of H plus, if you will. Okay, each base will represent a source of OH minus. But here, let's limit this to the acid first. So you have three different acids, water included, and what you notice here is that out of these three, you can pretty much say that water is weak, chlorous acid is stronger, and HF is the strongest. Okay, I'm not saying that, or we can start with weak, weaker, and weakest. Let's do that. Let's forget about this, because you have like a acidity constant, they are all weak, right? So this is weak, this is weaker, and this is the weakest. Okay, so that we don't make a mess with the strong acids here. Okay, in that scale, then whoever is stronger dominates. Okay, whoever is stronger controls the pH. Okay, let's write that down. Whoever is, not who, let's say whichever is stronger controls pH. Okay, and which one is stronger here? The hydrofluoric acid. So in this situation, the hydrofluoric acid controls the pH because it's the stronger acid that you have in the mixture. Okay, you can think in terms of, if you have the chlorous acid, it's 10 to the negative 8 versus 10 to the negative 4. There are 4 orders of magnitude, so 10,000 times larger constant. That means that the contribution from chlorous acid to the contribution of hypochlorous acid is this. Contribution of hypochlorous acid is 10,000 times smaller, and we haven't touched water yet. Okay, there is 10 orders of magnitude regarding the contribution of water. So HF controls pH, meaning that if you are going to calculate a pH and you have those three equations, you're going to pick the one with the largest Ka, and you will completely ignore the other two. Okay, because there's nothing to contribute from those equilibria. Okay, so this is how you work acid equilibria. It's pretty much the same setup every single time. There would be some other considerations that you can make if you have a kind of an initial concentration of the acid, so in which you have to consider the contribution of the other acid, but for now we are not going to worry about that. Okay, so that's it for now.